Welcome to Science to Sleep By, where we journey into the mysteries of the cosmos with calm voices and thoughtful wonder, giving your mind a universe to dream about as you drift into rest. Tonight, we'll explore two of the most distant and frozen worlds in our solar system, Uranus and Neptune. These ice giants, silent and far away, orbit in the cold reaches of space. But how far are they? And just how cold can a planet really be? Let's begin our journey. When we speak about the planets of our solar system, we often imagine the ones most familiar to us. Mercury, hot and racing close to the sun. Venus, shrouded in thick clouds. Earth, our home, alive with blue oceans and green lands. Mars, the rusty desert world where humanity dreams of visiting someday. Beyond these, we encounter the giants Jupiter with its great red storm and Saturn with its shining rings. But far beyond even those familiar giants, in the cold reaches of the solar system, lie two worlds that are different from the rest. Uranus and Neptune, the ice giants, sit quietly at the edge of our cosmic neighborhood, waiting for us to notice them. They are not as well known as the other planets, but their story is one of distance, coldness, and mystery. The name ice giants already paints a picture in your imagination. Unlike Jupiter and Saturn, which are called gas giants because of their overwhelming size and composition, Uranus and Neptune are smaller, denser, and made of materials that freeze solid in the cold conditions of deep space. When astronomers first studied them, they realized that these planets were made not only of hydrogen and helium gas, but also of water, methane, and ammonia in large amounts. These substances, in the bitter cold of space, behave like ices, and so Uranus and Neptune earn their unique title. The colors of these planets are the first things that strike us. Uranus, with its soft pale greenish-blue hue, looks serene and quiet in the telescope's gaze. Neptune, deeper in color, shines with a rich, vibrant blue, like the color of the ocean under a clear sky. The striking difference in their shades, though subtle, speaks of their atmospheres and the gases within them. Methane gas plays a key role, absorbing the red light of the sun and reflecting the blues back toward us. From Earth, hundreds of millions of miles away, we see them as glowing jewels in the black sea of space. To truly appreciate what Uranus and Neptune represent, we must imagine their place in the solar system. The sun, blazing at the center, pours light and warmth outward in all directions. Close by, that light is strong, as it is on Earth, where life thrives in the balance between warmth and cold. Mars, farther away, receives less warmth, and its deserts stretch beneath thin skies. Jupiter and Saturn, though far, are still touched by the sun's strength. But Uranus and Neptune orbit at distances so great that the sun appears as nothing more than a bright star, tiny compared to what we see in our own sky. Sunlight, by the time it reaches them, is weak, faint, and almost delicate. That faint light falls across their clouds and their storms, illuminating them in a twilight that never ends. Uranus, the seventh planet from the sun, was the first planet ever discovered with a telescope. In 1781, the astronomer William Herschel was scanning the heavens when he noticed a point of light that seemed unusual. At first, he thought it might be a star, but its motion across the sky revealed the truth. It was a new planet, one never known to ancient stargazers. This was the beginning of our awareness of the ice giants. Neptune came later, in 1846, not by chance, but through mathematics. Astronomers had noticed Uranus behaving strangely in its orbit, tugged by the gravity of something unseen. By predicting where that unseen planet should be, they found Neptune, almost exactly where calculations had said it would be. These discoveries expanded humanity's view of the solar system, revealing that the family of planets extended farther than anyone had imagined. From the start, Uranus and Neptune seemed different. Uranus spins on its side, tilted at an angle of nearly 98 degrees. No other planet behaves this way. Its seasons are unlike anything on Earth. Imagine a planet where the poles, rather than the equator, face the sun for years at a time, then fall into years of darkness. This odd tilt may have come from a colossal collision in the distant past, leaving Uranus forever tipped over. Neptune, on the other hand, does not have such an unusual tilt, but it does hold mysteries of its own. Its winds, the fastest recorded in the solar system, roar through its atmosphere at incredible speeds, more than 1,000 miles per hour. Even in the deep cold, Neptune is restless, alive with storms and motion. Though they are called twins, Uranus and Neptune are not identical. Uranus is slightly larger, but Neptune is denser and more massive. Uranus is calm in appearance, with few visible features in its atmosphere. Neptune, however, is dynamic, with dark storms and swirling clouds that change over time. These differences intrigue scientists and add to the mystery of why two planets, formed in similar regions of the solar system, can behave so differently. From a human perspective, these planets feel impossibly remote. To stand on Earth and look up at the night sky, we see stars that are unimaginably far away, but the planets in our own solar system feel closer, more connected. Yet Uranus and Neptune remind us that even within our own system, distances grow vast and cold. These are places we have visited only once briefly, when Voyager 2 flew past them decades ago. That spacecraft gave us our only close-up images, fleeting glimpses of what lies there, before continuing on into the deeper darkness beyond. Since then, Uranus and Neptune have remained distant and unexplored, glowing softly in the telescope's view, as though reminding us that the universe still holds more questions than answers. In the story of our solar system, Uranus and Neptune are the quiet guardians of the outer frontier. They are not as showy as Jupiter with its storms, or Saturn with its rings, but they are unique. They show us another kind of planet, one made not just of gas, but of ice and strange chemistry. They remind us that the solar system is not uniform, that each world has its own character, its own history, and its own secrets. And as we drift into thought about them, we sense the beauty of diversity among planets, the endless variety that the universe creates, the balance between similarity and uniqueness, between closeness and distance. Their name, ice giants, also carries an almost poetic weight. Giants, because they are massive, far larger than Earth, yet small compared to Jupiter. Ice, because they embody coldness, stillness, and silence, qualities that echo through their faraway orbits. To think of them is to think of vast skies of pale blue and deep azure, where the sun is no more than a shining dot, where time passes differently, and where the silence of space is broken only by winds racing at unimaginable speeds. These are worlds of extremes, yet also worlds of beauty, symbols of distance and of the deep cold that defines the outer reaches of our home system. To understand Uranus and Neptune, one must first come to terms with their distance from the sun. The sun is the heart of our solar system, the source of warmth and light that sustains life on Earth, and the anchor around which every planet orbits. Its gravity reaches across billions of miles, holding each world in its invisible embrace. The closer a planet is to the sun, the faster it circles. Mercury, for instance, completes its orbit in just 88 days, a quick runner around the solar track. Earth, sitting at an average of 93 million miles from the sun, takes a year to make its way around. But Uranus and Neptune move at a pace so slow, over distances so great, that their orbits stretch into centuries. Uranus, the seventh planet from the sun, lies at an average distance of 1.8 billion miles. In astronomical units, the measure astronomers use to make sense of vast spaces, that is about 19 AU. One astronomical unit is the distance between Earth and the sun. So Uranus is 19 times farther than we are. To imagine this, picture standing on a vast, open plain. If the sun were a lamp burning brightly in the middle, Earth would be a cozy house just down the road. But Uranus would be a small cottage far out on the horizon, barely touched by the glow of that central flame. The warmth that feels abundant here on Earth dwindles to a faint trace out there, just enough to touch the clouds of Uranus with a pale glimmer. Neptune, the eighth and farthest planet, carries the concept of distance even further. On average, it lies about 2.8 billion miles from the sun. In astronomical units, Neptune's orbit is 30 times the distance of Earth's. That number alone can feel abstract. So let's bring it into perspective. Sunlight, which races at nearly 186,000 miles per second, takes just over 8 minutes to travel from the Sun to Earth. That same light must travel more than 4 hours before it finally reaches Neptune. Imagine light itself, the fastest traveler in the universe, taking hours to cross the gulf between the Sun and Neptune. If you were standing on Neptune, looking toward the Sun, it would appear no larger than a bright star in the sky, far smaller and fainter than we see it from Earth. The daytime on Neptune would not feel like our daytime at all. It would be a twilight world, bathed in dim light, with shadows stretching long across icy clouds. Comparisons help bring these distances closer to our imagination. Let us think about Earth's orbit as a neighborhood street. If Earth's path around the Sun were just 1 block long, then Mercury would circle close, like a child running tight around the lamppost. Mars would be only a few houses away. Jupiter would already be at the edge of the street, a walk that feels long but still manageable. Saturn would be across the field at the end of town. But Uranus and Neptune would be past the borders of that town altogether, sitting in distant countryside, far removed from the warmth of the central light. They belong to the outskirts, the far neighborhoods where silence rules and the Sun is a distant beacon. This remoteness is reflected in their orbits. Uranus takes 84 Earth years to complete a single lap around the Sun. That means if you were born on Uranus, you would have to live nearly an entire human lifetime before celebrating one birthday. Neptune, even farther out, takes 165 Earth years for one orbit. When it was discovered in 1846, Neptune had not yet completed a full trip around the Sun, and it did not do so until 2011. In a human sense of time, these orbits are vast and slow, stretching across generations. Entire eras of history can pass on Earth while Uranus and Neptune quietly drift through just a fraction of their journeys. To travel there, even in thought, requires stretching the imagination. If you were to drive a car at highway speed, perhaps 60 miles per hour non-stop, without ever resting, it would take more than 3,000 years to reach Uranus, and closer to 5,000 years to reach Neptune. Even the fastest spacecraft built by humanity, such as Voyager 2, which left Earth in 1977, took 9 years to reach Uranus and 12 years to pass Neptune. Despite traveling at speeds of tens of thousands of miles per hour, distance in the outer solar system is not measured in hours or days, but in decades and lifetimes. But these enormous numbers are not just abstract. They shape everything about Uranus and Neptune, from their temperatures to their atmospheres and even their mysteries. The farther a planet is from the Sun, the less energy it receives. The faint warmth that reaches them is only a tiny fraction of what Earth receives. At Uranus, the sunlight is less than 1/400th as strong as it is here. At Neptune, it is less than 1/900th. Imagine standing under the midday sun on Earth, feeling its warmth on your skin. Now imagine that light dimming, fainter and fainter until it becomes weaker than the glow of twilight. That is the sunlight Uranus and Neptune receive every day of their endless years. The distance also gives them a sense of isolation. While Earth feels connected to its neighbors, Mars a close companion, Venus shining in the evening sky, Jupiter visible as a bright star, Uranus and Neptune drift in solitude. Their next nearest neighbor is billions of miles away. Communication with Earth takes hours. A radio signal traveling at the speed of light, the fastest thing known, still requires more than 2.5 hours to reach Neptune. When Voyager 2 sent back its images of Neptune, every photograph, every burst of data, took that long to return home. The planets live in a realm where even light itself cannot bridge the distance quickly. This great distance is one of the reasons Uranus and Neptune remain so mysterious to us. While we have sent multiple missions to Mars, orbiters to Jupiter, and probes to Saturn, we have visited the ice giants only once, and only in passing. The sheer challenge of sending a spacecraft so far, across billions of miles, means that missions are rare and precious. We rely heavily on telescopes here on Earth, straining to capture what little light reaches us from these distant worlds. Much of what we know about Uranus and Neptune comes from brief glimpses, careful measurements, and the courage of imagination, and yet, their distance also makes them fascinating. In that remoteness lies a reminder of scale, of how vast our solar system truly is. The distances between planets grow not in a straight line, but in leaps. With each successive orbit farther and farther from the Sun, it is almost as though space itself is stretching outward, placing these planets in the quiet reaches where only the patient eye of a telescope can follow them. To contemplate their distance is to contemplate the size of the solar system, and to realize that our home, our familiar Earth, occupies just a small corner of a much larger expanse. When we try to understand the enormous distances of Uranus and Neptune, it often helps to compare them with what we already know our own world, Earth, and the neighboring planets that feel closer and more familiar. Our planet is the yardstick by which we measure so much in astronomy. Earth, at 93 million miles from the Sun, is the baseline, the home from which we look outward. The light that warms our oceans and paints our skies travels from the Sun to Earth in just over 8 minutes. That seems almost immediate, the blink of a cosmic eye. It is that same measurement, the Earth-Sun distance, that astronomers call 1 astronomical unit, or AU. When we say that Uranus is 19 AU from the Sun, or that Neptune is 30 AU, we are essentially saying they are 19 and 30 times farther from the Sun than we are. But what does that really feel like? Imagine first the difference between Earth and Mars. Mars is our neighbor outward from the Sun, and it lies about 1.5 AU away. Already, the difference in warmth is noticeable. While Earth is filled with lakes and forests, Mars is a cold desert, with thin air and ice locked away in its soil. Mars is a place we can imagine visiting, perhaps even living upon one day. But its environment is far harsher than Earth's. That is only half again the distance from Earth to the Sun. Now extend that comparison farther, to Jupiter. At about 5 AU, Jupiter receives only a fraction of the sunlight we do. If Earth's skies are bright and warm, Jupiter's are dim and shadowed, with sunlight spread thin across its massive atmosphere. Beyond Jupiter lies Saturn, at roughly 10 AU, already so far that its rings gleam in faint, distant light, glowing but not blazing. And then, after a wide gulf, come Uranus and Neptune. Compared to Earth's 1 AU, Uranus at 19 AU and Neptune at 30 AU are worlds removed. Not just neighbors down the street, but distant relatives across the country, of sight. Living under entirely different conditions, if we were to compare the time it takes light to reach these worlds, the difference becomes clearer. Earth, as we know, receives light in 8 minutes. Mars, a short trip outward, gets light in about 12 minutes. Jupiter's clouds are illuminated by light that has traveled 43 minutes from the Sun. Saturn waits more than an hour for its light. Uranus receives its sunlight in about 2 hours and 40 minutes. Neptune, the loneliest planet, receives it in over 4 hours. So while we bask in the warmth of the Sun, almost instantly, Uranus and Neptune must wait, their skies glowing with light that has been on a long journey through space before it finally touches their frozen atmospheres. In comparing them to Earth, we can also think of the way the Sun itself would appear. On Earth, the Sun is vast in our sky, a brilliant disk that dominates the day. On Mars, it looks slightly smaller, as though viewed through tinted glass. On Jupiter, the Sun would appear tiny, not much larger than a bright star. By the time you reach Uranus, the Sun is a pale dot, still brighter than the stars around it, but no longer the overwhelming presence it is here. At Neptune, it is smaller still, a jewel-like point of light in a dark, endless sky. If you stood on a cloud deck of Neptune and looked upward, you would not see a blazing sun, but a distant spark, fragile and remote. There is another way to compare Uranus and Neptune with Earth, and that is through the scale of travel. Imagine that Earth's orbit around the Sun were the size of a single step you could take with your own feet. If you took that one step, you would have walked from Earth to the Sun. To walk from the Sun to Mars would take a step and a half. To Jupiter would take 5 steps. Saturn would be 10. To reach Uranus, you would need 19 full strides, and to reach Neptune, 30. You can imagine the long walk, each step taking you farther from warmth and light, until by the time you arrive at Neptune, you stand in a shadowed field, far removed from the glowing center. This simple picture gives us a way to imagine the scale of space, not in millions or billions of miles, but in the rhythm of steps, each one stretching the imagination farther outward. Comparing Uranus and Neptune with Earth also reminds us how much smaller and warmer our own world is. Earth is a rocky planet, solid beneath our feet, wrapped in a thin layer of atmosphere that sustains us. Uranus and Neptune, by contrast, are made mostly of gases and ices. Their atmospheres are thick, their surfaces hidden beneath layers of clouds and storms. If Earth is a warm, familiar home with oceans and continents, Uranus and Neptune are vast, stormy seas of methane and water vapor, with no firm ground to stand upon. The warmth of Earth feels intimate and abundant compared to the deep cold of those ice giants, while our planet maintains a delicate balance. Warmed enough by the sun to hold liquid water, Uranus and Neptune drift so far away that even gases we think of as familiar water vapor, ammonia, methane, condense into ices under their frozen skies. To place this in perspective, imagine if Earth were moved outward to where Uranus resides. Our oceans would freeze solid, our atmosphere would collapse into ice crystals, and life as we know it would vanish into the silence of cold. If Earth were shifted all the way to Neptune's orbit, our planet would become little more than a frozen ball, reflecting the faint light of the sun as it circled in silence. Earth, in many ways, is defined by its position, close enough to the sun for warmth, far enough for stability, uniquely balanced between fire and frost. By comparing Earth to Uranus and Neptune, we see how fragile that balance truly is. The outer planets also remind us of how human time and planetary time differ. On Earth, a year is a comfortable cycle. We experience the turning of the seasons, the return of spring, the passage of summer into autumn, and the quiet cold of winter. That rhythm shapes our lives, our histories, and our memories. But on Uranus, 1 year lasts 84 hours. On Neptune, a year lasts 165. Imagine being born on Neptune and knowing you would not live long enough to see your planet complete a single trip around the sun. Entire human civilizations could rise and fall while Neptune made its slow journey. Compared to our fast, familiar orbit, their movement is glacial, almost timeless. Looking at Earth from the vantage of Uranus or Neptune also changes our perspective. From here it feels vast mountains, oceans, skies that stretch forever. But from the icy giants, Earth is nothing more than a point of light, a pale blue dot shining faintly near the sun. To us, they are distant worlds, strange and mysterious. To them, we are the tiny, fragile one, circling close to the warmth of a star. The comparison humbles us, reminding us that our sense of scale depends on where we stand, and that distance itself reshapes our understanding of what is large and what is small. The deeper we move into the solar system, the colder and quieter the worlds become. Earth, sitting close enough to the sun to be warm and alive, is blessed with a balance of energy that keeps water liquid and air breathable. Mars, farther out, is cooler, its atmosphere too thin to hold much warmth. Jupiter and Saturn drift even farther, where sunlight grows weaker and weaker, but both of them keep part of their heat through their enormous size, still radiating warmth from their ancient beginnings. Yet as we travel outward, past Saturn's shining rings, into the darker parts of the solar system, we arrive at Uranus and Neptune, the ice giants. Their very name suggests what they are: frozen worlds, where cold dominates, where temperatures plunge to extremes that earthly imagination struggles to hold. On Uranus, the average temperature sinks to about -350 degrees Fahrenheit. This is not a kind of cold we know here on Earth. Even in the bitter winters of Alaska or the snowy fields of the Midwest, where night winds cut to the bone and ice forms on the ground, the air is still hundreds of degrees warmer than the atmosphere of Uranus. It is a realm where warmth is absent, where molecules move slowly, where the sun's light arrives faintly and carries almost no heat to soften the chill. If you could somehow stand within its atmosphere, though you would be crushed by the pressure, the cold would be absolute, surrounding you in silence, as though the very energy of life had been drained away. Neptune, though even farther from the Sun, is slightly warmer than Uranus, with average temperatures around -330 degrees Fahrenheit. This small difference, only about 20 degrees, might not sound like much, but it carries a mystery. Neptune's greater warmth does not come from the Sun, which shines more weakly there than at Uranus. Instead, Neptune produces its own heat, releasing more energy than it receives. Somewhere deep within its layers, the planet holds onto ancient warmth, or perhaps processes we do not yet fully understand, churn and radiate energy outward. This makes Neptune restless and stormy, with winds faster than any on Earth, racing across a frozen landscape that somehow still has motion. To put these temperatures into perspective, we can compare them to familiar extremes on our own planet. The coldest temperature ever recorded on Earth was in Antarctica, about -128 degrees Fahrenheit. That number alone feels almost unimaginable. A cold where steel becomes brittle, where breath freezes, where survival depends on protection and shelter. And yet, Uranus and Neptune are more than 200 degrees colder still. Their average atmosphere is a place so frigid that water, the substance we think of as fluid and life-giving, would be as hard as rock. Ammonia, methane, and other gases we know as invisible or faint on Earth become ices under such conditions. These planets are laboratories of cold, where matter itself behaves differently, where familiar rules bend under the pressure of low temperatures. The cold also shapes the appearance of these planets. The methane in their atmospheres absorbs red light and reflects blue, giving Uranus its pale aqua hue and Neptune its deeper sapphire glow. But that same methane, chilled to extremes, forms hazes and clouds that blanket the planets in layers of icy mist. In photographs taken by Voyager 2, Uranus appeared almost featureless, a calm green-blue sphere floating against the black of space. Some of that stillness comes from the cold, from an atmosphere so sluggish that it hides its storms. Neptune, in contrast, shows swirling features, storms darker than their surroundings, bands of movement that streak across its face. The contrast between the two ice giants, one calm and subdued, the other active and fierce, is a reminder that cold does not always mean stillness. Beneath Neptune's chill exterior, energy still surges, driving winds that cut across the frozen silence. When we think of cold, we often imagine it as absence of warmth, absence of light, absence of life. But the cold of Uranus and Neptune is something more. It is a presence in itself, a defining force that sculpts their identity. On Earth, cold is seasonal, temporary, something that comes and goes. Winter yields to spring, and even in the darkest nights, warmth is not far away. But on the ice giants, cold is permanent, eternal, unrelenting. It is the background against which everything else exists. This is not just a matter of numbers. The physics of extreme cold reveals strange behaviors. At such temperatures, gases condense into liquids or solids. Materials that are invisible on Earth, like methane, which gives natural gas its faint odor, become major components of the atmosphere and climate. Clouds on Uranus and Neptune are not made only of water vapor, but also of methane ice, ammonia crystals, and other exotic substances, floating in the frigid skies. The cold creates alien weather systems, patterns unlike anything we know, where storms are born not from heat rising, but from energy stored in the planet's core, battling against the overwhelming chill of space. If one could drift slowly into the atmosphere of Neptune, wrapped in protection, the descent would be into layers of increasing cold. High above, the sunlight barely filters through, a dim glow in the haze. Lower down, the cold is sharper, the wind stronger, until finally, the pressures rise and the chill settles into an unrelenting freeze. The same is true for Uranus, except its skies are quieter, its storms more subdued, as if its extreme tilt and its lost heat have left it in a deeper stillness. In both worlds, the cold is not just temperature but character, defining the atmosphere, the color, the chemistry, and even the mood of the planet. For us on Earth, cold carries meaning. It brings to mind nights by the fire, frost on windows, breath visible in the air. But these are human experiences, shaped by a narrow range of temperatures. The cold of Uranus and Neptune exists beyond human touch, beyond any environment where life as we know it could survive. It is a reminder of the fragility of our warmth, of how rare and precious Earth's balance truly is. To compare our world with theirs is to see how extraordinary it is to live on a planet where liquid water flows, where sunlight is abundant, where warmth is constant and reliable. In the silent cold of the ice giants, there is no such comfort. Only the endless freeze of distance, the unbroken reign of low temperatures that shape entire worlds. When we look at Uranus and Neptune through the eyes of a telescope, what strikes us first is their color. Unlike the pale beige of Jupiter or the golden tones of Saturn, Uranus and Neptune appear in shades of blue, quiet and otherworldly. Uranus shows a gentle turquoise, soft and muted, while Neptune glows with a deeper sapphire, rich and intense. This striking appearance comes not from their surfaces, for they have no solid ground we can stand upon, but from the vast oceans of gases that surround them. Their atmospheres, thick and mysterious, tell the story of their identity. To understand these planets, one must first understand the chemistry of the skies that cloak them. The air we breathe on Earth is made of nitrogen and oxygen, clear and invisible. But the atmospheres of Uranus and Neptune are entirely different. They are composed mainly of hydrogen and helium, the two lightest and most abundant elements in the universe. These gases form the bulk of the planets, just as they do in Jupiter and Saturn. Yet what sets Uranus and Neptune apart is the presence of another element, methane. Though it makes up only a small fraction of their atmospheres, methane is what gives the ice giants their signature color. Methane absorbs red light from the sun, allowing only blue light to escape. From Earth, what we see reflected back is that cool, calming glow, like sunlight filtering through a deep, frozen sea. But these atmospheres are not just colors in the sky. They are layered and complex, with clouds and hazes stacked upon one another, each made of different substances depending on the pressure and temperature. In the upper reaches of Uranus, the atmosphere is dominated by hydrogen, helium, and traces of methane. Lower down, the cold grows more intense, and methane condenses into icy clouds. Beneath those clouds, deeper still, lie possible layers of ammonia and water, also crystallized in the freezing conditions. Neptune follows a similar pattern, but with a key difference. Its storms and winds churn the atmosphere with greater vigor, mixing the gases, shaping clouds into patterns that shift and change. Voyager 2, when it passed Neptune in 1989, captured images of the Great Dark Spot, a storm almost as large as Earth itself, swirling across the blue planet. This storm, like Jupiter's Great Red Spot, was born of atmospheric dynamics, a dance of gases moving under pressure and energy. If one could descend into these atmospheres, it would be like entering a vast ocean of gases, each layer stranger than the last. The upper air would be thin, faintly blue, and frigid. As you fell deeper, the haze would thicken, the pressure mounting, the cold, turning even familiar gases into unfamiliar forms. Clouds of methane ice crystals would drift like frozen smoke, silent in the darkness. Ammonia ice might form deeper down, mingling with water in ways that would seem impossible on Earth. The deeper you sank, the less the atmosphere would resemble air at all. Instead, it would feel like plunging into an alien sea of exotic chemistry, a place where there is no ground to reach, only endless transitions from gas, ice, to liquid-like states that blur the boundaries we know. This layering of gases and ices is why scientists call Uranus and Neptune ice giants, rather than gas giants, while Jupiter and Saturn are made almost entirely of hydrogen and helium. Uranus and Neptune contain far more water, ammonia, and methane in their interiors. These ices, frozen in the cold of deep space, define their composition, though we cannot see beneath their upper layers. Scientists believe much of their bulk consists of icy materials under immense pressure, forming strange phases of matter unlike anything on Earth. There may be oceans of water mixed with ammonia, hidden beneath thousands of miles of atmosphere. Heated not by sunlight, but by the energy of the planets themselves, the atmospheres of Uranus and Neptune are also home to winds unlike any on Earth. On Neptune, the winds reach speeds of more than 1,200 miles per hour, faster than the speed of sound. These winds whip across a planet colder than any place we can imagine, stirring its methane-rich skies into storms that last for years. Uranus, quieter in appearance, still holds winds that circle at hundreds of miles per hour, though its tilted axis makes its weather patterns unlike any other planet. Its atmosphere experiences long seasons, each lasting decades, with one hemisphere bathed in faint sunlight while the other lies in near total darkness. These conditions sculpt the clouds into patterns that shift slowly over time, too subtle to see at a glance but persistent over years. The role of methane cannot be overstated. On Earth, methane is a trace gas, present in small amounts, yet powerful in its effects on climate. On Uranus and Neptune, methane is far more abundant, shaping not only the colors we see, but also the chemistry of the atmosphere. Under the influence of ultraviolet light from the sun, methane molecules break apart and recombine, forming hazes and complex hydrocarbons that float in the upper atmosphere. These hazes soften the light, adding to the pale or deep tones that distinguish Uranus from Neptune. They also influence the heat balance of the planets, trapping or reflecting energy in ways that scientists are still trying to understand. And yet, for all that we know, there is so much we do not. The atmospheres of Uranus and Neptune have been studied mainly from afar, through telescopes and brief flybys. Voyager 2 remains the only spacecraft to have visited them directly, and it could only capture fleeting glimpses as it raced past. The thickness of their atmospheres, the exact distribution of their gases, the hidden processes within their depths, these remain mysteries. Some scientists believe that deeper within, under crushing pressures, exotic forms of ice may exist, including what is called superionic water, a phase where water molecules break apart and ions move freely, creating materials that are both solid and liquid at once. Others speculate that lightning storms may flash through the hidden clouds, sparks of energy in the frozen dark. The atmospheres of Uranus and Neptune also play a role in their magnetic fields. Unlike Earth, whose magnetic field is aligned closely with its axis, the fields of the ice giants are tilted and offset, as if twisted by the dynamics of their interiors. The movement of conductive materials deep within their atmospheres may generate these unusual fields, wrapping the planets in magnetospheres that behave unlike any others in the solar system. The strange tilt of Uranus, knocked sideways long ago, makes its magnetic field even more unusual, spinning and shifting in ways that puzzle scientists. To think of these atmospheres is to think of alien skies. Imagine standing, if it were possible, on some floating platform within Neptune's upper layers. Above you, the sun would be a distant point, barely shining. Around you, the sky would be a rich blue, darker than Earth's, lit not by brilliance, but by depth. Winds would race silently past, too fast to feel, carrying clouds of methane ice like frozen breath. Deeper below, unseen, would be storms larger than continents, swirling through the dark. On Uranus, the sky would be calmer, its color a paler green-blue, its clouds more subdued. But the tilt of the planet would make the seasons unlike anything we know. With years of strange daylight followed by years of shadow, the atmospheres of Uranus and Neptune are not just layers of gas. They are living systems, dynamic and ever-changing, shaped by chemistry, physics, distance, and time. They are windows into the history of the solar system, relics of the primordial materials from which the planets formed. They are reminders that even in the farthest reaches of space, where cold dominates and light is scarce, motion and energy still exist. Sculpting beauty out of silence, the balance of energy is what defines a planet's personality. For Earth, the warmth we feel, the winds that move through our skies, and the water that flows across our lands all come from a delicate exchange between sunlight arriving from space and heat radiating outward into the dark. Too much energy trapped and the world grows too warm. Too little, and it freezes. This balance is not just about temperature. It is about the rhythm of existence itself. When we turn our gaze toward the ice giants, Uranus and Neptune, we see a story of energy that is as strange as it is silent. One written in the faint light of a distant sun, and in the hidden warmth of planetary hearts that still glow faintly from their ancient beginnings. By the time sunlight reaches Uranus, it has traveled nearly 2 billion miles. It is so far from the sun that light there is about 400 times weaker than it is on Earth. What we call daylight on Uranus would look more like twilight to us, a faint glow instead of a bright blaze. Neptune lies even farther away, almost 3 billion miles from the sun, where sunlight is almost 900 times weaker than what reaches our world. Imagine standing beneath the midday sky on Neptune. The sun would appear not as a blazing disk, but as a small, pale star, so distant that its light feels more like a memory than a presence. With so little sunlight, it is natural to imagine that these planets are frozen to the core. Yet the truth is more complex. Despite their distance, both Uranus and Neptune reflect much of the sunlight that does reach them, their clouds and hazes scattering light back into space. Their pale blues and deeper sapphires are the result of methane absorbing the red and letting the blue escape. But beneath the colors lies a faintly shimmering truth. Sunlight plays only a minor role in shaping their climates. On Earth, sunlight drives winds, storms, and seasons. On Neptune, sunlight is so weak that it could never account for the raging storms that sweep across its surface. Something else must be at work, something from within. Neptune, particular, puzzles scientists. Despite its distance, despite its frigid atmosphere, it radiates more than twice as much energy as it receives from the sun. This means Neptune is glowing with its own inner heat, an echo of its formation billions of years ago when the planet coalesced out of the dust and gas of the young solar system. Back then, countless impacts, gravitational compression, and the slow settling of heavy elements would have heated its interior. While much of that energy has dissipated over time, Neptune still releases a steady warmth, not enough to thaw its frozen atmosphere, but enough to stir it, to drive its winds, and to fuel its massive storms. This hidden energy makes Neptune alive in a way that Uranus is not. Its weather patterns are restless, its clouds ever shifting, its storms temporary yet powerful, some appearing and vanishing within mere years. Uranus, by contrast, seems quiet, almost unnaturally so. It radiates almost no excess heat, giving off about as much energy as it receives. This makes it the coldest planet in the solar system, even colder on average than Neptune, despite being closer to the sun. The mystery of Uranus is why. Why does Neptune retain its heat while Uranus does not? Some scientists suspect that Uranus, long ago, suffered a catastrophic collision with a massive object, perhaps the size of Earth itself. Such an impact might have knocked Uranus onto its side, tilting it 98 degrees relative to its orbit, but it may also have disrupted its core, scattering or redistributing the heat in such a way that it no longer escapes efficiently. If this is true, then Uranus's silence is not just atmospheric, but historical, the quiet aftermath of a planetary trauma in energy and tilt. The way a planet handles heat is tied deeply to its structure. Beneath the clouds of Uranus and Neptune lie layers of ices, not like the ice in our freezers but exotic forms of water, ammonia, and methane under crushing pressures. As one moves deeper, the pressure grows so extreme that ordinary rules of matter bend. Water, for example, may enter a strange state known as superionic ice, where oxygen atoms form a solid lattice but hydrogen ions move freely, making it both solid and fluid at once. This bizarre form of matter may conduct electricity, and if so, it could help explain the unusual magnetic fields of the ice giants, which are tilted and offset in ways unlike Earth's. If such exotic ices move and shift inside the planet, they may also transport heat outward, but in Uranus's case, something about that process seems stalled or muted. The outer atmospheres of these planets tell us more about their energy balance. On Neptune, high-speed winds faster than 1,200 miles per hour race across the frozen skies. Storms larger than Earth appear, swirl, and then vanish, fueled not by sunlight, but by the hidden heat rising from the deep. Voyager 2 captured the Great Dark Spot, a storm the size of our planet, with bright methane clouds nearby, like high cirrus clouds on Earth. Later, telescopes on Earth saw the storm fade, replaced by others, as if Neptune's weather is in constant motion, restless and unending. Uranus, when Voyager 2 passed it in 1986, appeared bland and featureless, a smooth, pale orb with few visible storms. Yet more recent observations with the Hubble Space Telescope and ground-based observatories have revealed that Uranus does have activity, especially near its equinoxes, when sunlight briefly spreads more evenly across its tilted poles. Still, compared to Neptune, Uranus remains subdued, its atmosphere strangely still, as though its lack of inner heat has quieted its weather. Energy balance also affects the seasons of these distant worlds. On Earth, our tilt of 23 degrees gives us the familiar rhythm of spring, summer, fall, and winter. Uranus, tilted almost completely on its side, experiences seasons that last decades. For nearly half a Uranian year, about 42 Earth years, one pole faces the sun in unending daylight while the other lies in darkness. Then, slowly, the situation reverses. This extreme tilt means that its energy from the sun is distributed in the strangest ways, with some regions bathed in faint light for decades and others starved of it for just as long. How such a planet balances its internal and external energy is one of the ongoing puzzles of planetary science. Neptune, less tilted at about 28 degrees, has seasons more similar to ours in concept, but with each season lasting over 40 years. These drawn-out cycles mean that weather changes we observe are measured not in days or weeks, but in decades and centuries. When we think about energy on Earth, we think of warmth, of sunlight on our skin, of fire crackling in a hearth. But on Uranus and Neptune, energy is subtle, hidden, and slow. It moves not in bursts we can feel, but in gradual flows of heat rising from unimaginable depths, in winds that circle a frozen world at supersonic speeds, in storms that rage across the coldest skies in the solar system. Their balance of energy is unlike anything familiar, yet it is a balance nonetheless, one that has endured for billions of years, shaping planets into the quiet ice giants we see today. To understand Uranus and Neptune, one must first grasp the vastness of space itself. The sun, which feels so close and ever-present to us here on Earth, is a furnace of light and warmth that governs the entire solar system. Its gravity holds the planets in orbit, and its energy defines the conditions of their skies. Yet, as you move outward, farther and farther from its central glow, the influence of the sun diminishes. What seems overwhelming at Earth becomes faint at Uranus, and almost ghostly at Neptune. Their stories are not only about chemistry or temperature, but about distance, the staggering gulf that separates them from the sun, and the way that gulf transforms light into something almost otherworldly on Earth. We take for granted the brilliance of sunlight. At midday, it is dazzling, casting sharp shadows, lighting landscapes with vibrancy. Even on cloudy days, there is an abundance of light. But Uranus lies nearly 1.8 billion miles from the sun, and Neptune is even more remote, at about 2.8 billion miles. Numbers like these are so large that they can feel abstract, but we can measure them in light itself. Sunlight takes only 8 minutes to reach Earth. To arrive at Uranus, it must travel for about 2 hours and 40 minutes. To reach Neptune, it journeys for over 4 hours. In that time, it spreads, weakens, and fades until what once blazed as brilliance becomes the faintest of glows. Imagine standing on Earth at dusk, when the sun is low on the horizon, and the light grows soft, shadows long and dim. Now imagine that level of dimness, not as a fleeting moment, but as a permanent condition. That is what midday sunlight feels like on Uranus. On Neptune, the effect is even stronger, more like twilight, the kind of light we associate with the quiet of evening. For an observer used to Earth's brightness, The sun seen from Neptune would not look like a blazing disk, but like a brilliant star, far brighter than the others in the sky, but still small, distant, and pale compared to what we know. The dimness of light shapes everything about these distant planets. For one thing, it means that their energy cannot come from sunlight alone. On Earth, sunlight warms the ground, drives the winds, and powers life through photosynthesis. On Uranus and Neptune, sunlight is too weak to fuel such processes. The skies are not ruled by the sun, but by the hidden heat within, by the dynamics of gases and ices, and by the immense distances that filter the energy down to almost nothing. Sunlight there is like a whisper compared to the voice it carries here. The way light scatters through their atmospheres also changes how we see them. On Earth, the blue of the sky is created by Rayleigh scattering, where molecules in the atmosphere scatter short wavelength light more effectively than long wavelengths. On Uranus and Neptune, methane in their atmospheres absorbs red light, allowing mostly blue and green wavelengths to escape. Combined with the faint sunlight, this creates skies that are not only dimmer, but colored in strange, serene shades. Neptune glows with a dark, rich azure, as though the faintness of the sun has concentrated its color. Uranus shines with a softer, more subdued aquamarine, its distance lending it a muted, almost ghost-like quality. Seasons, too, are shaped by distance. On Earth, our year lasts 365 days, a direct result of the distance we orbit from the sun. Uranus takes 84 Earth years to complete a single orbit. Neptune takes 165. A person born on Neptune would never see a full Neptunian year, even if they live 2 of our lifetimes. Because of this distance, their seasons are stretched to extremes. Uranus's tilt of nearly 98 degrees means that for decades, one pole faces the sun in dim, unending daylight, while the other lies in shadow. Neptune, less tilted, experiences long, slow seasons where the changes in light are almost imperceptible, stretched across generations. On both worlds, the faint sun still governs the rhythm of time, but in a way that is alien to our short, sharp cycles. The reduced light also affects the landscapes we imagine. Though Uranus and Neptune lack solid surfaces, we can imagine floating in their upper atmospheres, gazing upward. The sun, small and far away, would shine weakly, surrounded by a sky darker than Earth's. Stars, even in daytime, would be visible, piercing through the thin glow of twilight. The Milky Way would stretch across the heavens in clear detail, uninterrupted by the scattering brightness of sunlight that hides it here. To stand in such a place would be to see the galaxy not as something distant and faint, but as a constant presence, a river of light running across a sky that is always dark. The planet's remoteness gives them skies where the universe itself is laid bare. For spacecraft, the distance means delay. Signals sent from Earth to Uranus take over 2.5 hours to arrive. To Neptune, they take over 4 hours. Communication across such distances is not like talking on a phone, but like sending a message into the past, waiting long hours for a reply. For astronomers, this delay is a reminder of just how far away these planets are, how separated they are from the warmth and immediacy of our world. The dimness of their sunlight is matched by the silence of their distance, a quiet that feels almost eternal. The psychological effect of such distance is profound. When we imagine visiting Uranus or Neptune, we must imagine a world where light itself is scarce, where darkness reigns and the sun is but a faint lantern in the sky. For humans, so used to the abundance of light on Earth, this would be disorienting, perhaps unsettling. Yet in another way, it would be deeply calming. The constant twilight of Neptune, the endless softness of its light, could create an atmosphere of quiet unlike anywhere else. A place where the rhythms of time slow and the sharpness of daylight fades into something eternal. For Uranus, decades of steady dimness would create an almost meditative environment, a reminder that even planets can live at a slower pace than our hurried lives on Earth. Distance also means isolation. The farther a planet lies, the less energy it receives, but also the less connected it feels to the center of the solar system. Jupiter and Saturn are still close enough that the sun dominates their skies. Uranus and Neptune, by contrast, live on the edge, where the sun is no longer a constant but a faint companion. Beyond Neptune lies only the Kuiper belt and the scattered disk, regions of icy debris. Farther still lies interstellar space. In this way, Neptune especially feels like a border planet, a sentinel standing guard at the edge of the sun's domain. Its faint light levels are not just a scientific fact, but a symbol of remoteness, of being almost lost in the dark, and yet, even at these distances, the sun still matters. The faint light that reaches Uranus and Neptune is enough to illuminate them, enough to give them color, enough to shape their long seasons and subtle climates. The whisper of sunlight, so faint compared to Earth, still threads through their atmospheres, still touches their clouds, still keeps them bound to the same cycle of day and night, dawn and dusk, that unites the planets of the solar system. When we think of weather on Earth, we think of familiar cycles. Warmth from the sun drives air currents, winds stir across land and sea, clouds gather and dissolve, rain falls, and sometimes storms thunder through the sky. All of it is powered by sunlight and shaped by our atmosphere's balance of gases. On Uranus and Neptune, however, the story of weather is written differently. Their skies are far colder, their sunlight is faint and weak, and their atmospheres are composed of gases unfamiliar to our daily lives. Yet, paradoxically, their weather is some of the most extreme and powerful in the solar system. The ice giants, though quiet from afar, harbor winds faster than hurricanes, storms larger than continents, and weather systems that evolve not over days, but across decades. Uranus and Neptune, though both called ice giants, do not share the same level of activity. Uranus, when Voyager 2 visited in 1986, appeared strangely calm. Its pale aqua disk showed only the faintest signs of cloud features, almost smooth, as though the planet were wrapped in a blanket of silence. Neptune, by contrast, when Voyager 2 reached it in 1989, displayed swirling clouds, dynamic storms, and shifting patterns that made it appear restless, alive, and full of motion. This contrast puzzled scientists, for both planets share similar compositions and structures. The difference lies not only in their heat, but in how their atmospheres respond to the forces within them. Neptune is the most turbulent of the two. It is home to the fastest winds ever recorded in the solar system, reaching more than 1,200 miles per hour. These winds howl through its frigid skies, moving faster than the speed of sound relative to the atmosphere. On Earth, winds of even a few hundred miles per hour are catastrophic, tearing down trees, buildings, and landscapes. On Neptune, such speeds are routine, part of the planet's daily weather. The cause of these supersonic winds remains a mystery. With so little sunlight to drive them, scientists believe the energy must come from Neptune's internal heat. As the planet radiates more energy than it receives, this warmth rises, stirs, and sets the entire atmosphere in motion, creating a dynamic and violent weather system that dwarfs anything on our world. One of Neptune's most famous features was the Great Dark Spot. Discovered by Voyager 2, it was a massive storm, nearly the size of Earth, swirling in Neptune's southern hemisphere. Like Jupiter's Great Red Spot, it appeared as a vast oval, a whirlpool of winds and clouds. Yet unlike Jupiter's centuries-old storm, Neptune's was fleeting. Within a few years, it had vanished, replaced by other dark spots that appeared and disappeared in different locations. This suggests that Neptune's atmosphere is far more changeable, with storms that rise from the depths and dissolve back into them over relatively short spans of time. These storms are not gentle. They are accompanied by bright methane clouds, frozen crystals forming high in the atmosphere, riding the currents like cirrus clouds above a hurricane. They move with the winds, gleaming against the darker background of the storm. Uranus, in comparison, is subdued. For decades, it was thought to be almost featureless. Its extreme tilt, lying almost on its side, gives it unique seasons that last for decades. During its long summers and winters, one pole faces the sun continuously while the other remains in shadow. This unusual orientation may contribute to its quiet appearance, with energy distributed in a way that dampens atmospheric motion. However, modern telescopes, particularly the Hubble Space Telescope and powerful observatories on Earth, have revealed that Uranus is not as still as Voyager's single visit suggested. At times, especially near its equinoxes when sunlight is more evenly spread across the planet, Uranus has displayed bright storms, massive enough to be seen from millions of miles away. These storms are thought to be driven by deep processes within the atmosphere, perhaps aided by seasonal shifts, showing that even Uranus has moments of restless weather hidden beneath its calm facade. The chemistry of these atmospheres contributes to the weather we see. Methane, abundant in both planets' skies, not only gives them their colors, but also plays a role in cloud formation. When methane cools, it condenses into icy crystals that form bright clouds high above. Ammonia and water may form deeper clouds, though hidden beneath the haze. On Neptune, these layers combine to create contrasts of light and dark, bands of swirling storms, and fleeting features that drift across the planet in a matter of days. On Uranus, the clouds are fewer and subtler, blending into the pale atmosphere. Yet, when storms do appear, they can be surprisingly intense, with bright plumes rising from the depths, visible even across billions of miles. The winds themselves are astonishing. On Neptune, they circle the planet at incredible speeds, westward near the equator, and eastward near the poles, creating bands of movement that interact to spawn vortices and storms. On Uranus, winds also flow rapidly, up to 500 miles per hour, though more subdued than Neptune's violent gales. These winds, blowing through an atmosphere so cold and tenuous, would be utterly alien to human senses. There would be no familiar feel of moving air, no sound of rustling leaves or waves stirred by breezes. Instead, the winds of Uranus and Neptune exist in silence, whipping clouds of methane and ammonia in patterns invisible, except to distant eyes. The scale of time in these weather systems is also unlike anything on Earth. Our storms come and go in days or weeks, even the strongest hurricanes, lasting only a matter of weeks at most. On Neptune, storms can endure for years, shaped by slow-moving currents and deep energy sources. On Uranus, decades-long seasons may influence the appearance of storms, with weather patterns tied not to days or months, but to vast stretches of planetary time. This slowness, the sense of weather unfolding at a pace beyond human lifetimes, is part of what makes the ice giants so fascinating. The contrast between Uranus and Neptune reminds us that weather is not only a product of sunlight. On Earth, the sun dominates, driving evaporation, winds, and climate. On Neptune, the sun is too far away to provide such power. Its storms and winds are fueled instead by heat from within, by the slow release of energy stored since the planet's birth. Uranus, with its muted heat, shows us the other side of the balance, an atmosphere subdued, quiet, and still. Together, they illustrate the different paths a planet can take, how similar compositions can produce such divergent skies. To imagine standing within these weather systems is to imagine an alien experience. Floating high above Neptune's clouds, one would see towering storm systems stretching farther than continents, winds racing faster than any hurricane, and lightning perhaps flashing in the depths below, illuminating methane clouds in bursts of light. On Uranus, the view would be calmer, the pale sky stretching into dimness, with storms appearing only as distant plumes, occasional outbursts breaking the monotony of the still atmosphere. Both worlds are harsh and inhospitable, but their weather is a reminder of how dynamic even the coldest, farthest planets can be. The winds, storms, and weather patterns of Uranus and Neptune reveal not just the extremes of planetary atmospheres, but also the endurance of motion in the most unlikely places. Even on the edges of the solar system, where sunlight is weak and cold is unrelenting, the skies are alive. They are restless, ever-changing, shaped by forces hidden deep within. Forces that remind us that energy, in one form or another, continues to shape worlds, no matter how far away they drift. As we have slowly drifted outward across the solar system tonight, our journey has taken us far from the warmth and familiarity of Earth's skies. beyond the bright giants Jupiter and Saturn, into the quiet, dim realm of Uranus and Neptune. These two distant ice giants remind us that even in the coldest, darkest places, the universe is never truly still. They sit on the edge of the sun's reach, bathed in pale blue light, their atmospheres frigid and strange, yet still alive with winds, storms, and subtle patterns that unfold across decades. We have reflected on their immense distances, where sunlight takes hours to arrive, and the warmth of our star is no more than a faint whisper. We have traced the bitter cold of their atmospheres, where methane clouds form in crystalline layers and temperatures drop lower than any place we know on Earth. We have explored the vastness of their atmospheres, the mystery of their internal heat, and the delicate balance between silence and motion that sets them apart from each other. So as you close your eyes tonight, let Uranus and Neptune drift into your imagination. Picture their pale blue and deep indigo hues, their silent storms, their winds racing endlessly through alien skies.